is Jason. Thanks for having me here. And I'm going to kind of talk about capacitive tactile sensors. So I was kind of shocked to learn that most people actually don't know what tactile means. And one of my colleagues told me that. I said, what do you mean? He's like, for 20 years I've been using the term tactile. So could I see a raise of hands where you feel comfortable, you know, what tactile means? That's a very unusual or good audience because, you know, people think about textile. You mean textiles or, you know, tactical or, you know, it's very, I don't know. But I've been using the term tactile for over 20 years because my initial sort of research is in robotics, but through that I started a company called PPS, and we really focus on sort of more interesting, innovative applications for our sensor technology. So we do design and development of custom sensors, but also work with OEMs on embedding our sensor technology, as well as other services. So 1996 is when I graduated my PhD in robotics, to give robots a sense of touch. So going from university research of understanding grasp kinematics and sort of how to use tactile sensing, how to grasp things gently without breaking it, without dropping it, to our first project was actually funded by Rick Satava at Diaper. He was interested in actually measuring what surgeons do during surgery to develop training simulation tools. Obviously, it's kind of difficult to kind of practice on patients, so they were developing these simulators, but they didn't really know what a good surgeon did. So our very first project, nearly 20 years ago, was to develop a glove for that a surgeon could use. And it's an example of what we start off with. One of the challenging things about putting a sensor on the hand is that it's very sort of highly dexterous or sort of a lot of moving joints. And so to get the performance out of the sensor, we have to kind of encase it in a rigid sensor structure, as you kind of see there, sort of very limited. So when I was finishing, my advisors actually suggested that, you know, your research is kind of interesting, but maybe those sensors will be useful, you know. And so they kind of encouraged me in that direction without really having a good understanding of the market or the, you know, where it could be used. So here, what I call kind of my MBA of hard knocks, going into business without really understanding where the market opportunity is. So over the years, you kind of see it's interesting to kind of go back. There's actually a website called archive.org or something like that that captures all the web pages over time. So it's that fun sort of going back to the years to kind of look at different stages of the company development. And I guess looking at it, I realized probably our marketing is still not really good because it doesn't give you a good grasp of what we do. But these are some of the customers that we work with, more sort of recognizable brands. And I guess I'm glad that many of you understand tactile, but I want to kind of sort of explain sort of my sort of learnings or differentiation from pressure mapping or for thin film force sensor type of what I mean by tactile, because pressure sensors, MEMS-based pressure sensor, any kind of pressure sensor is a scalar value, you know, same pressure everywhere in this room, for example. We also know that force sensors, you know, have this kind of vector quantity. But what do you do when you have 1,000 sensors on a surface that's not flat, that's on a curved body surface, you know? And so here's an example where it's a press. It's a pneumatically operated heat press that we have in our lab, and there's a pressure gauge, right? So you laminate things with it with heat and pressure. Now that pressure gauge is actually the air pressure to move the plate up and down, right? And so the amount of force that it generates is based on the pressure, but it's actually also dependent on the size of the piston cylinder, right? So that's pretty straightforward. But what's the actual pressure that you're laminating these two materials with? You know, that's a lot more complicated because that plate is pretty large, so it's actually not the same pressure as the pressure that's shown on the pressure gauge. I was kind of shocked that one of my engineers actually thought that the pressure displayed was actually the contact pressure. I said, you know, I gotta educate this. So if you have a small object that's in there, you know, the amount of contact area of that object is going to be much smaller, and so it's going to be a much higher pressure than if you have a bigger object. But where tactile sensing is important is that, let me put it maybe more easily understandable kind of context, is that whether you're sitting on a soft couch or whether you're sitting on a hard bench, the weight of your body is the same, and the contact area of your rear end is pretty much the same too, right? But it's a lot more comfortable sitting on a couch because of the conforming of the foam that reduces the pressure peaks and whatnot. So that's where we, use our sensor technology. So our technology is based on capacitors. So two electrodes that are separated by a gap form a capacitor, if you remember sort of physics days. And what we do is we actually put a compliant layer that compresses with pressure. So as the gap gets closer, the capacitance changes, and we measure that. Now, it's a very small gap and a very small amount of capacitance. We're able to resolve down to femtofarads. And then we can implement that in an array configuration, multiplexed or single element for OEM application where you don't need that many sensors. This is a nice video that kind of shows the difference between capacitive touch sensors you're all familiar with, which a lot of people get confused in terms of what we have. So here's a demonstrator that shows the different types of sensing technology: traditional mechanical switch, capacitive touch sensors that's on your screens, and our capacitive force sensors. This is a single element, so force sensing. So as you're aware, a lot of the accidental activation issues with touch screens, because it's actually detecting the electrical properties of your finger. Mechanical switches don't have that. Capacitive force sensors, because it's mechanical, don't have that accidental switching issue. Like with this glove on, I can't really actually use my touchpad on my laptop here, but you can do that with capacitive force sensing. And also it works in harsh environments like when it's getting wet. So proximity sensors are sensitive to water, and we're inherently insensitive to environmental condition changes. On top of that, we give you proportional information, so it's not just an on-off. So one of the challenges the automotive industry has is that they've been trying to implement capacitive touch with limited success, and we believe that this type of technology can be a value add to their solution. So here's some sort of the overview of the type of pressure ranges that we work with. Up to 700, actually we're right now doing a automotive brake application where it's like 1400 PSI, very high pressures, down to very low pressures where the human body is around a PSI or so, for a comfort type of fit, garment assessment type of things like the headsets and whatnot. But we also have been able to extend beyond sort of the actual pressure regime, where people are interested in detecting particles. So a dispersion of perfume spray, you can actually capture the particle dielectric properties of the materials rather than actual pressure. Because when you have a suspension of particles, there's really no pressure because it's sort of suspended. Imagine a cloud, if you will. So over the years, we worked with a lot of different types of materials. Conformable cloth that can be molded and shaped to different shapes, to stretchable cloth materials like Lycra that literally stretch, which is very good for human interface type applications. For industrial applications or very thin sensor requirements, we have more polyimide, high temperature, high pressure type of applications. A lot of OEM applications kind of require both. We talked about sort of combining flexibility with electronics. So what we call a hybrid uses the FPCB for the electronics, but also uses a flexible or conductive cloth material, so you get more flexibility than other laminates. So we've been pretty much sort of under the radar, I think, when I saw Roger's list of companies, and we went on the list. It's like, hey, you know, what's going on? I need to get out there and share people about the advantages of capacitive sensor technology. So the key point here is that there's been a lot of FSRs, conductive inks materials, and the problem with that approach is that for pressure sensing or force sensing is that those two materials, when they make contact, at a microscopic level, the inks get damaged, right? So every time you make contact, there's some level of degradation that happens because it's mechanical. So the properties of that sensor changes over time. If you're just doing, you know, research paper and you need to collect your data and you're done, then that's fine. But to embed a product, you need more stability. Then having two electrodes that never touch is a lot more repeatable, more stable. And because with these resistive sensors that go from a no contact to contact state at the low pressures, they're not very well behaved at the low pressure levels. And so, which is not the case with capacitive. So the two key things that I'd like you guys to take away is that capacitive you know, tactile sensors are more repeatable and more sensitive than FSR type of technology. There are limitations. I'm not trying to just pitch our technology being the best. The worst thing in terms of sensor performance, we don't compared to load cell type of and MEMS type of sensor performance, we really fall short on creep. Typical sensors that we have are about 1% full scale range creep over 1 minute. We have developed and demonstrated sensors with 0.1%. The other area that, because capacitive sensing is more difficult, takes longer. So typically it's slower than FSRs. But we did develop a sensor that has 1,920 elements at 220 Hertz update rate. So we're able to do that with parallel processing. The other disadvantage with our sensor has been sort of the cost. We typically shoo away university grad students that want to ask about how much our sensors cost. And so to address that issue, we actually recently launched a product called SingleType. It's very comparable cost to the FlexiForce, and it's a toolkit for people to experiment with, to do feasibility type of experiments. So, focusing more on human pressure mapping, you know, comfort with protective hearing equipment for work areas, as well as many of the audio headset companies are interested in fit and comfort. And so we were able to actually take our conductive cloth type sensors and mount it onto a human mannequin head so that we have a reference, but actually conform to that two-dimensional curvature. So when we say flexibility, a lot of times, you know, people talk about printed flex and, you know, films that are flexible, but only in one direction. So the term that I use for two-directional flexibility that we need for human body is conformability. So as you see, this sensor that's really wrapped around the mannequin head conforms and provides very sensitive pressure information. For the women in this audience, the fit and comfort of bra is very important. And so we've had manufacturers that actually asked us to develop a mannequin that can actually evaluate where the pressure source or pressure spots are for the wire or the snaps or fittings on there. So that was a challenging project because of the number of sensors that required for very high resolution because of small features, but also very low pressures. Talked about diapers. So this is going back quite many number of years, but consumer product companies are obviously very interested in leakage of diapers, and they want to monitor the seal, but they also don't want to over-pressurize and make it uncomfortable. So we've been able to develop sensors that can be wrapped around, not sort of live babies, but mannequins that can actually be articulated and moved to see where the gaps are formed using our sensors. We have a number of other projects of putting sensors on mannequins, for protective gear type of things, to sort of a training tool for doing sort of pat-downs, to actually consumer product company that want to sort of optimize their shower head design. So a lot of projects going on there. There's a lot of applications or companies kind of focused on the foot, and we've done our share too. This was kind of a fun project that we did with Red Bull, of actually putting foot sensors, insole sensors on a surfer. The challenges of having electronics on a foot is, pretty difficult, in the sense that there's a lot of stretching and flexing and bending that's going on. But on top of that, we actually had to deal with the fact that it had to be waterproofed. And so we did this project with Red Bull in 4 months to go from concept paper to actually having McFadden, one of the world champion surfers, to put it on to assess and evaluate his surfing technique. And if you think about it, everything in surfing has to do with how you control the pressure on your feet to maneuver or control the surfboard. So that was a very interesting project. Interesting, we're not really actively a foot insole pressure sensing company. But over the years, as I've alluded to earlier, we've been coming back and over again on the hand, pressures on the hand. Interestingly, I'll teach you a little bit of Korean here. The word for hand in Korean is son, okay, S-O-H-N, which is actually my last name, ironically. So I don't know if it's karma or what, but I've been working on this for quite a while. This is our very first sort of conformed contact sensor. So this sensor was actually molded in the shape of a fingertip, so you could put it on there, put a finger cot, and measure pressures. Analog output, very single element. We have a product called Finger TPS that is purchased quite a bit by researchers because it's very conformable. You put this on, this is a lycra spandex type of material, so it's very minimally invasive. And if you have, this looks okay with just 2, but I've seen researchers put 12 sensors on the hand and a lot of wires, and so it's not very user-friendly. But and so now we have the glove, which has a lot more sensors, left and right hand wireless connectivity, and and so here's some experiments that we did actually, just to kind of see what we can do with it, and I think it's going to be a pretty useful tool for product developers. Here you're looking at the difference between having this is a light sort of weight drill, lithium-ion battery or not, and so when you're grasping it, you don't really need to hold it as heavily as a heavier battery drill that's shown here over time. And it also shows you where you're contacting the drill. So, I think as a product developer, I think you'd be really interested in that. We have our sales guy getting a massage all of a sudden, and you can see the difference in the pressures that's being used. The green line is the peak pressures, and the red line is the average pressure that the hand is exerting. You can see that most of them are sort of more on the fingertips, if you want. So here's me with a tennis racket. Used to play tennis a long time ago, but I still have the racket. So a lot of sports athletes I think would be interested in understanding how to hit a longer drive or a better putt, or how to control their performance with analyzing the hand contact pressures. So so we have been actually embedding our sensor technology into commercial products. So this is one of our first spin-off company called Sierra Scientific Instrument. With NIH funding, we developed this catheter that has 36-element pressure sensors. So you get a visualization of what happens in the esophagus when you swallow. before we had our sensors, the doctors only had like 4 of these traces, and they had to kind of piece together where they were located. And if the nurse didn't place the sensor exactly at the right location, then you had to do the procedure again. It was not a very pleasant procedure because this catheter goes through your nostrils and down the esophagus. So by making this product, you know, actually the technology is in the catheter, you know, enabling 36 sensors to be going inside a 1/4-inch catheter is phenomenal. But the value to the market was the ease of use. The software made this system so much more easier to use, so it really became the market leader very quickly and was acquired by a company now, Medtronic's, has the product. We also worked, one of the things that we're probably don't do a good job of marketing is that we're not just a sensor company, but as it was alluded to earlier, you know, it's not just about the sensor. The challenge is in actually integrating the sensor. And with tactile sensors, I think there's even more challenges because it's intimately in contact with the object. How you integrate is a big challenge. And so we worked with a company called eSoles to not just to do the tactile mat down below that you see the color map here, but we actually developed the whole system, controlled, computer control, sort of, this is a bladder that you put your feet in, it inflates, it has infrared sensors to determine the position, and then when it was in the right position, it actually did a 3D scan. We're able to extract that data to get the foot size and the arch height, and tremendously improve their first-time success on making a custom orthotic. Another company spun off product SureTouch. It's for breast cancer screening. Just like what a physician does for detecting lumps, you know, this device does it much more accurately because it's objective, it's more sensitive. Has FDA clearance, we have a fair bit of clinical data. We now recently got reimbursement approval, and we have a new CEO that's a MD, who's been a phenomenal transformation in getting the product marketed or discussing with the MDs as to how the product should be used. So, with that, thank you very much.